Okay, so this is example 6 from section 4.5. And I've drawn a little picture here just to get us going. So we're given that a rectangular page is to contain 24 square inches of print. So this area in here is meant to represent the area of the page that has print on it. And that area is 24 square inches. The margins at the top and bottom of the page are to be 1.5 inches. So this margin and this margin are both 1.5 inches. And then the margins on the left and the right are 1 inch, which my picture is probably not to scale, but you get the idea. So the side margins are 1 inch each, and then the top and the bottom are 1.5 inches. So the big question here is, what should the dimensions of the page be so that the least amount of paper is used? So we're solving for dimensions, but that doesn't really tell us what we're trying to optimize. The part that tells us what we're optimizing is this last piece of the statement, so that the least amount of paper is used. Well, to me, that means that we're trying to minimize the area of the paper. So we're going to need to come up with an area equation for the paper as our optimization equation. Okay, so we need to label our picture a little bit better. There are different ways that you could approach labeling this. We're trying to figure out the dimensions of the page. So the way that I'm going to do it is I'm going to say, again, there are different ways you could label. I'm going to say that this is X inches. So the width of the actual printed area is X inches. And the length of the printed area is Y inches. Or other way around. Maybe that's I don't know which would be longer. So length and width, X and Y for just the printed region, which that would make this side of the page X plus 2 inches. And then that would make this side of the page Y plus 3 inches. Okay, and the reason we would have X plus 2 is we would be taking X and we would be adding those 1 inch margins, which there's 2 of them. So that gives us X plus 2 inches. And then to come up with the Y plus 3, that would be the Y, the side Y for the printed region, and then plus the 2 1.5 inch margins gives us Y plus 3 inches. So then I can say that the area of the total page would be X plus 2 times Y plus 3. And we are trying to minimize the area, which means that this is our optimization equation. And notice that we have X and Y's in there, right? So area is right now in terms of dependent on what X and Y are. So we're going to need a secondary equation. And the secondary equation we could come up with could be for the printed area. So since we know that the printed area is going to be 24 square inches, that means that 24 is equal to x times y. And then solving for one of the variables, it doesn't matter which one. Like if we want to solve for y, we could have y equals to 24 over x, okay, to use as our secondary equation. And remember, our secondary equation then allows us to rewrite our optimization equation in terms of a single variable. So I am going to rewrite my area equation just to have more space. I'm going to rewrite it down here. So area would be equal to x plus 2, replacing the y with 24 over x. And then we have the plus 3. And we can differentiate as is, or we could multiply out our area equation and then take the derivative. It's kind of your preference. I guess I'll multiply out. So x times 24 over x would actually just end up being 24 because those x's would cancel. And then distributing x to the 3, oops, I passed the 3, to the 3 would be 3x. And then distributing 2 to 24 over x would be 48 over x. And plus 6. Okay, combining like terms, as well as rewriting that 48 over x as 48 times x to the negative first, just to make it easier to think about applying power rule. So this becomes 30 plus 3x plus 48x to the negative first. So a prime, our derivative of our area equation, our optimization equation, is going to be 3 minus 48 times x to the negative second. And to rewrite our derivative without a negative exponent, that would be 3 minus 48 over x squared. And if you remember, I've told you guys for finding critical values, when we have a fraction in our derivative, we want to get that written as a single fraction. So I'm going to think about writing as multiplying the 3 by x squared over x squared to get a common denominator. So a prime is equal to 3x squared minus 48 divided by x squared. I'm going to give myself an extra page as well. Okay, so for finding critical values, I'm going to set the numerator equal to 0 and solve. Okay, so 48 divided by 3 ends up being 16. Okay, so then x is plus or minus 4, right? This is for trying to find our critical values. We're not sure. These are the possible critical values. And then we also have the denominator set equal to 0, and that would end up just being x equals to 0. And I've told you guys, you could check for the constraints when you first write your optimization equation, or I always end up doing it after I've identified my possible critical values, because that's just usually when I think about it, but it's whatever your preference is. So going back up to our picture, and I have my area equation defined in terms of x. So thinking about the restrictions of x and y, all we can really say is that x and y have to be greater than 0. If x was 0, we'd have 0 printed area. I'm going to say just x is strictly greater than 0 because I don't have a maximum value that x could be. So I can't define my optimization equation on a closed interval, which means we're going to use the first derivative test for identifying our absolute extrema. So coming back down here, this allows me to throw out, and then also, actually I'm not going to include 0 for sure because look at my optimization equation. Right? 0 can't be in the denominator. 0 would make my area equation undefined. So that actually helps us. We can throw out 0. We can also throw out the negative. So 4 is going to be our critical value. And when we use our first derivative test, we'll make our analysis line. I'll put 4 on there as our critical value, and I'm also going to put 0 at the end as an endpoint. So choosing test values, I can use 1, I could use 5, and plugging those test values into the derivative. So if I plug 1 in, right, that ends up being 3 minus 48, which will definitely be a negative value, so it'll be decreasing. And then if we plug 5 in, well, 3 minus 48 divided by 5 squared. Oops, I typed that in wrong. I get 27 over 25, which is positive. So the graph would be increasing. So the graph is going to, between 0 and 4, be decreasing and then switch to increasing, which means from 0 to infinity, which is the interval for which our optimization equation is defined, x equals to 4 is actually going to be the location of our absolute minimum, right? Just using first derivative test in general, that tells us that x equals to 4 is the location of a local minimum. But if we do that extra step of analysis and think about the domain of our optimization equation, x equals to 4 would actually be the absolute minimum. No, it wouldn't be the absolute minimum. It would be the location of the absolute minimum. Sorry. And then just going back up to the word problem and double checking what we're solving for. We want to know the dimensions of the page. So we can use 4 and plug it into the x plus 2. So 4 plus 2 is 6. So we'd have 6 inches. And then we need to figure out what y would be. And to figure out what y would be, we could plug in x into our equation for y that we came up with from the secondary equation. So y equals to 24 divided by 4, which is 6. So y would be 6, and we could think about plugging 6 into the y plus 3. So the dimensions of the page would actually be 6 inches by 9 inches, or the length would be 9 inches, the width would be 6 inches. We weren't actually asked for the minimum area, we were just asked for the dimensions. So we can say to minimize the amount of paper used, right? Reword what the question is. The paper or the page must be 9 inches by 6 inches or something like that. And that would be our summary for this problem.